All right, today we are journeying deep, deep inside our own planet. But we're not using a drill, we're using supercomputers. We're going to see exactly how scientists are building a virtual Earth to understand the massive, slow-motion engine that drives our entire world, the mantle.
And that, right there, is the central problem, isn't it? The Earth's mantle is thousands of kilometers of solid rock under heat and pressure that we can barely comprehend. We can't send a probe, we certainly can't send a person, so how on earth do we know what's going on down there?
Well, the answer is scientists build a planet from scratch, inside a computer. And we're going to follow that process, step by step, building our understanding just like they build their models. First, we'll look at what these virtual planets even are. Then we'll fire up the basic engine, throw in a massive complication that creates these wild quasi-avalanches, check out a competing theory, and finally tackle the biggest challenge of them all, plate tectonics.
So, since we can't just look at the mantle, scientists have to get creative. They create what are called numerical models. You can think of them as these unbelievably complex simulations that are basically solving the fundamental laws of physics for how heat and rock should flow, but on a planetary scale.
You know, the first attempts at this were essentially 2D slices, kind of like a simple sketch. But scientists realized pretty fast that this was a huge problem. The real mantle doesn't work in flat little planes. The key features we see evidence for, like the long sinking sheets of crust we call slabs, and the rising columns of hot rock called plumes, these are fundamentally 3D structures. To get it right, you have to model the whole shebang, the entire sphere.
Okay, so let's start simple. Let's look at the most basic version of one of these 3D mantle models. What are the absolute fundamental forces that get this whole planetary engine running in the first place?
It all comes down to one word: convection. And it's the exact same process you see in a pot of soup heating on the stove. The hot stuff at the bottom expands, gets less dense, and rises up. Then the cooler, denser stuff at the top sinks to take its place. Now just imagine that your soup is actually rock, the pot is the size of a planet, and the whole process takes millions and millions of years.
So in these basic simulations, two really clear patterns just pop out. The hot, rising material, it naturally organizes itself into these incredible column-like structures. These are the famous mantle plumes, what we think are the sources for volcanic hotspots like Hawaii.
And of course, what goes up must come down. The cold's denser material, sinking from the surface, doesn't form columns. Nope, instead, it creates this connected, linear network of downwelling sheets. This is the model's version of tectonic plates, subducting, or diving back into the Earth. So you get this elegant system, hot columns rising, cold sheets sinking. But it's just too simple to be the real story.
So now let's see what happens when we add another layer of real-world physics. Because when scientists factored in just one more detail, this nice, elegant system was thrown into complete chaos. And that's when it got a whole lot more interesting.
That new piece of physics is something called a phase transition. See, deep inside the Earth, the pressure is so intense that it actually forces the atoms and minerals to repack themselves into a tighter, denser structure. The most critical one of these happens at a depth of 660 kilometers. For a cold, sinking slab of rock, hitting this boundary is kind of like hitting a false bottom in our giant soup pot. It really resists being pushed through.
And this barrier creates this absolutely dramatic sequence of events. First, the cold, sinking sheets hit this boundary, and they can't easily punch through. So they stall, and they start to spread out and pile up. But more and more material keeps coming from above, creating this massive, super dense pool of cold rock that gets heavier and heavier, until suddenly that barrier just can't hold it anymore. And the result is a catastrophic failure, a huge mantle avalanche that punches through and plummets all the way down into the lower mantle.
So this isn't a nice, steady process anymore. It is completely chaotic. These avalanches happen sporadically, in different places, at different times, and they are enormous events that suddenly flush these massive amounts of cold material from the upper mantle all the way down to the core mantle boundary, totally rearranging the flow of the entire system.
But hold on, this avalanche model, it isn't the only game in town. Some scientists think the key controlling factor isn't some sharp mineral barrier, but something much simpler: stickiness, or to use the technical term, viscosity.
So this brings us to two big, competing ideas. On one side, you have the phase change model, where that 660-kilometer barrier acts like a dam, which leads to these catastrophic dam-breaking style avalanches. But on the other side, you have the viscosity model.
This theory says that the lower mantle is simply much more viscous, about 30 times stickier, than the upper mantle. In this version, when a sinking sheet hits this thicker, stickier layer, it doesn't pile up and crash through. It just slows down, broadens out, and breaks apart into these big, slow, diffuse blobs. It's less like a dam breaking and more like trying to push thick tar through water.
So here we are. We have these incredible models that can simulate plumes and sheets and even these massive mantle avalanches. But even with all this complexity, there is one giant, glaring thing that's completely missing from our virtual Earth.
The models don't spontaneously create plate tectonics. The surface of these virtual planets is either one solid, rigid lid, or it's kind of a sluggish, mushy surface. They don't have distinct, rigid plates with sharp boundaries that smash into each other to build mountains or slide past one another to cause earthquakes. And getting that to happen, well, that's the holy grail of mantle modeling.
To solve this, scientists have to get the rheology right. It's a bit of a fancy word, but rheology is just the study of how a material deforms and flows. And the key is that the Earth's mantle has this kind of dual personality. Over millions of years, under immense pressure, it flows like incredibly thick honey. But if you apply a sharp, fast stress to it, it can be brittle and fracture, just like a candy bar. Capturing both of those behaviors in the mathematics is the real challenge. And the most promising idea right now is a property called strain weakening. It's a little counterintuitive, but it basically means that the more you deform a rock, the more you strain it, the weaker it gets in that specific area. And this creates a powerful feedback loop. Stress starts to focus in a narrow zone, which makes that zone weaker, which allows it to deform even more easily, which focuses the stress even more. This is the process that could create sharp, self-lubricating, plate-like boundaries out of what was once a totally uniform surface.
And this is the frontier. Models are just now beginning to bake in these incredibly complex rheologies. And for the first time, they're starting to see the first hints of plate-like behavior. The ultimate goal, the dream, is to create a model where you just plug in the laws of physics, hit go, and out comes a living, breathing planet, complete with continents, oceans, and self-generating plate tectonics. The quest to build a virtual Earth is far from over.